In this video, I'll explain about matrices and determinants. Let us see what is the definition of a matrix. Matrix is a rectangular array of numbers of functions. Array means it's a collection of numbers or functions. For example, if I consider 2 minus 3, 1, 0, 4, 5, then this is a collection of numbers and it is arranged in the rectangular form. We call this as a matrix. Now these horizontal lines are called as rows of the matrix and the vertical lines are called as columns of the matrix. So these form columns. So in this case there are two rows R1 and R2, two columns C1, C2, C3. The elements within this matrix are called as entries of that matrix. So the first row has 2 minus 3 1 and the second row has 0 4 5. First column has 2 0, my second column has minus 3 4, third column has 1 5. Matrices are denoted using capital letters like A equal to, B equal to, 1 0 minus 1 5 and so on. Now order of a matrix or size of a matrix is nothing but it is the number of rows and number of columns in the given matrix. Suppose if you have a matrix A of order m by n, that means there are m rows and n columns. M rows, n columns. Here in this case, there are 2 rows and 3 columns, hence it is of order 2 by 3. This is how to read 2 by 3. Now in this case there are 2 rows and 2 columns, hence order of the matrix is 2 by 2. So always rows first, columns next. So generally when you have a matrix A of order m by n, that means there are m rows and n columns. A m by n matrix is represented as A11, A12, so on up to A1n, because there are n columns, A21, A22, so on up to A2n, and here AM1, AM2, so on up to AMN. So which is equal to, in general, I can represent it as Aij, which is of order m by n. I ranges from 1 to m, j ranges from 1 to n, integers, all natural numbers here. This is because I is the row index, j is the column index. This means Aij means it is the element in the ith row and jth column. A11 means element in the first row, first column. A22 means element in the second row, second column. AMN means element in the mth row and nth column. This is how we represent a m by n matrix in a general way. Now there are different types of matrices. Types of matrix. A row matrix. Row matrix means it has only one row, which has order 1 by n. Any number of columns, but there is only one row. For example, 2 minus 1, 5. This is a matrix of order 1 by 3. There is only one row and 3 columns. Next, column matrix. Column matrix means it has only one column. It is of order m by 1. For example, 2 minus 1, 5. Or else even more, 6. So there are 4 rows and 1 column. It is of order 4 by 1. Next, square matrix. Square matrix means a matrix in which number of rows equal to number of columns, m equal to n. So it is of order m by m, or you can write it as n by m. Such a matrix is called as square matrix. Rectangular matrix means where m not equal to n, number of rows not equal to number of columns. Square matrix means if number of rows equal to number of columns, then we call that matrix as a square matrix, and it is of order m or order n. Anything is fine. For example, 2 minus 1, 5, 0. This is a square matrix of order 2 because there are 2 rows, 2 columns. Similarly, 1, 0, minus 1, 5, 4, 2, minus 1, 3, 6. This is a square matrix of order 3 because there are 3 rows and 3 columns. Now, any square matrix has diagonal elements or principal diagonal or main diagonal. So, the elements of the form A11, A22, A33, so on up to AMM, if it is of order M, then these elements are called as diagonal elements or principal diagonal elements. Only square matrix has these diagonal entries. Now, in this case, so these elements are diagonal elements 2, 0. Row index, column index same. So element in the first row, first column. Element in the second row, second column is diagonal element. Similarly here, element in the first row, first column, second row, second column, third row, third column. Therefore, diagonal elements are 1, 4, 6. Only for a square matrix we have diagonal elements or the principal diagonal, which is also called as main diagonal. Next type of matrix is diagonal matrix. Diagonal matrix means it is a square matrix in which all non-diagonal elements are 0. So these are called as diagonal elements. Other than these elements, the remaining elements are called as non-diagonal elements or off-diagonal elements. That is, Aij equal to 0 for all I not equal to j. I equal to j means diagonal elements. I not equal to j means non-diagonal elements. So, a square matrix in which all non-diagonal elements are 0 is called as a diagonal matrix. See, for example, I will consider 2 by 2 matrix 2, 3, 0, 0. So these are the diagonal elements. Then the remaining elements must be 0. Now one more 2, 1, 0, 5. This is not a diagonal matrix. This is because here non-diagonal entry, this entry is non-zero. It is 5. It should be 0 if you are saying it as a diagonal matrix. Similarly, an example for diagonal matrix 3 by 3 diagonal matrix 1 0 0 0 2 0 0 0 minus 5. So here diagonal elements are non-zero here. Non-diagonal elements are all 0. There is no condition on diagonal elements. Diagonal elements, some of them may be 0, may not be 0, but the condition is non-diagonal elements are 0. Here all non-diagonal elements are 0, hence it is a diagonal matrix. Now 1 0 0 0 2 0 0 1 minus 5. So this is not a diagonal matrix because here one non-diagonal entry is non-zero. Hence it is not a diagonal matrix. Next is a scalar matrix. It is a diagonal matrix in which all diagonal elements are equal. So example is 2 0 0 2. So all diagonal elements must be same. Non-diagonal are all 0. Similarly 3 0 0 0 3 0 0 0 3. This is also a scalar matrix. 2 0 0 3. This is not a scalar matrix because diagonal elements are not equal. Next, identity matrix. It is a scalar matrix in which all diagonal elements are equal to 1. So that is 1 0 0 1. This is identity matrix of order 2. 1 0 0 0 1 0 0 0 1. This is identity matrix of order 3. So identity matrix is denoted using capital letter I. IN means it is of order n. So this is the meaning of identity matrix. Next, zero matrix. Zero matrix. It can be of any order in which all the entries are 0. Need not be square matrix. This is an example for zero matrix or 0 0 0 0. So this is about different types of matrices. Now, two matrices are equal if corresponding elements are equal and they are of same order. The first condition is two matrices should be of same order. Second condition is corresponding elements are same. Then we say that the matrices are equal. So for example, if you have 2, 3x minus 1 and here you have 2, 3, 1 minus 1. Now these two matrices are equal if x equal to 1 because rest all elements are same. If x equal to same as this, then these two matrices become equal. This is about equality of matrices. Now I can have two more types in the types of matrices. They are upper triangular matrix and lower triangular matrix. Upper triangular matrix, it's a square matrix in which all the elements below the diagonal elements are zeros. See, for example, 2, 4, 5, 0, 1, 6, 0, 0, minus 1. Now, when you consider this matrix, this is the principal diagonal or my main diagonal. Elements, all the elements below this main diagonal must be 0. Upper means below the diagonal, reverse. Lower means above the diagonal. So upper triangular, because when you have, it is like a triangle now, these elements are non-zero. Upper triangular matrix is a matrix in which all the elements below the diagonal are 0. Lower triangular is a square matrix in which all the elements above the diagonal, principal diagonal, are 0. See, for example, 2, 0, 0, 1 minus 1, 5, 0, 1, 2, minus 1. So, in this case, this is the principal diagonal. Elements above the principal diagonal are all 0. Here, hence, it becomes a lower triangular matrix. This is upper triangular matrix. So the condition is only on the elements here below the diagonal. Here in this case, elements above the diagonal. Number about operations on matrices. There are like addition, different operations you can perform on matrices, subtraction, scalar multiplication, and then the multiplication or product of matrices. Multiplication or product of matrices. So addition, how to add two matrices. To add two matrices, the condition is first they should be of same order and then corresponding elements are added. Corresponding elements are added. In the case of subtraction also, they should be of same order, corresponding elements are subtracted. For example, I will give you two matrices. A is 2, 3, 1, minus 1, 4, 0. And the matrix B is equal to 1, 0, minus 1, 5, 3, 6. Now A plus B equal to, now A is of order 2 by 3, B is also of order 2 by 3, hence they are of same order. Now to add these two matrices, corresponding first element we added to the first and 2 plus 1, 3. Second to second, 3 plus 0, 3. 1 plus minus 1 is 0, minus 1 plus 5 is 4, 4 plus 3 is 7, 0 plus 6 is 6. This is A plus B. Now to subtract also, they should be of same order. Yes, they are of same order. Now corresponding elements are subtracted. First with the first element, 2 minus 1, 1. Then 3 minus 0, 3. 1 minus of minus 1, that is 1 plus 1, 2. Then minus 1 minus 5 minus 6. 4 minus 3, 1. 0 minus 6, minus 6. This is A minus B. So in the case of addition and subtraction, order of the answer is also same as the given matrix. Order won't change. Now scalar multiplication means every entry of the given matrix is to be multiplied with the scalar. Say for example, this is the given matrix A. K into A means every element of the matrix A is multiplied with the K. So I will give you the scalar K as 2 into A. 2. K is equal to 2. Every element, every entry is to be multiplied with the 2. 2 2s are 4, 4 3 2s are 6, 2 1s are 2, 2 into minus 1 minus 2, 2 into 4 8, and 2 into 0. So in this case also order won't change. This is how to do the scalar multiplication. If you have the scalar minus 2, then multiply every element with the minus 2. Next, product of matrices. In the case of product or multiplication of matrices, there is a condition. Two matrices A and B can be multiplied only if A is of order m by n and B is of order n by p. That means number of columns of the first matrix, if it is equal to number of rows of the second matrix, then only matrix multiplication A into B is possible. Otherwise A into B is not defined. So in the case of both square matrix of the same order, then there is no problem. You can directly go the multiplication. If they are of different order, and rectangular matrices of different order, in that case you have to always check is number of columns of first matrix equal to the number of rows of second matrix. For example, I'll give you a matrix A is 1 2 minus 1 0, B equal to 1 3 0 minus 1. So in this case A is of order 2 and B is of order 2. Number of columns of the first matrix equal to the number of rows of the second matrix. And in this case, the product AB is of order m by p. That is n equal m by p. Here 2 by 2. Answer is also of the same order AB. It is a 2 by 2 matrix. Let us see how to find out that. Here AB is defined. Take the first row, first column. So multiply the corresponding elements, then add the result together. 1 into 1, then plus 2 into 0. So every element in the column got over. Hence, go to the next column. Shift to the next column. In the answer also you shift to the next column. But we are not shifting the row. Row remains same. Only column gets shifted. So go 1 into 3 plus 2 into minus 1. Similarly, now I am going to second row. In the answer also come down. Then second row with this first column, minus 1 into 1 plus 0 into 0. First element with this first element, second to second. Then minus 1 into 3, second row, second column, plus 0 into minus 1. Now simplify this. This gives you 1. This is 0. 3 minus 2, 1. This is minus 1. This is minus 3. So this is the matrix AB. Here in this case the product is defined and the product is also a matrix of order 2 by 2. Now I'll give you one more matrix, that is 2 1, and it is of order 2 by 1, and B is of order 2 3 minus 1 1. This is of order 2 by 2. Can you define AB? So in this case AB is not defined because number of columns of the first matrix not equal to number of rows of the second matrix. So here first row and first column if you take, there is only one element, you see. First element first. Second element extra is there is no second element here, hence AB is not defined. So this is how we find the product of two matrices. So product of two matrices is defined only if number of columns of the first matrix equal to the number of rows of the second matrix. Otherwise the product is not defined. And product is non-commutative. AB need not be equal to BA. In few of the cases AB may be equal to BA, but in general AB is not equal to BA. This is how we define multiplication of matrices. Now what is transpose of a matrix? Transpose of a matrix is obtained by interchanging rows and columns of the given matrix. So suppose A equal to 2 minus 1 3 5 4 0. This is a matrix of order 3 by 2. Now A transpose is denoted as A dash, or which is same as A transpose, or small letter also use, that is equal to interchange rows and columns. That is row 2 minus 1, write it as column 2 minus 1, then 3 5 4 0. This is how we take the transpose of given matrix. Now it is of order 2 by 3. So any matrix M is of order M by N. After taking the transpose, it becomes of order N by M. This is how we take the transpose of a matrix. Now with the help of the definition of transpose of a matrix, we define symmetric and skew symmetric matrix. Symmetric matrix is the one where A dash equal to A. Transpose is same as given matrix, then such a matrix is symmetric. Skew symmetric means transpose is negative of the given matrix, then such a matrix we call it as a skew symmetric. See, for example, how to construct a symmetric matrix. Write 1, 2, 3, these elements. Then these elements should be same as this. Okay, minus 1, 0 if you have written here 0. Then now when you take the transpose of this matrix, 1, 2, 3, 2 minus 1, 0 and 3, 0, 2. Now check with the given matrix. It is same as the given matrix. Hence, this is a symmetric matrix. A dash equal to A. Now, skew symmetric matrix means to construct a skew symmetric matrix, the condition you have to remember is principal diagonal elements must be 0. These are all square matrices. A square matrix is said to be symmetric. A square matrix is said to be skew symmetric. We are defining symmetry and skew symmetry only for square matrices. So 0, 0, 0. Diagonal elements must be 0. Then the off diagonal elements. If you have 1 here, in this place you have minus 1. If you have 2 here, then in this place you should have minus 2. And 3 here, in this place you should have minus 3. So that this A dash, if you take 0, 1, 2, then minus 1, 0, 3, then minus 2, minus 3, 0. Now compare it with the given matrix. The same as the given matrix, but these entries are multiplied by minus 1, so it becomes minus of A. That means symmetry means when you fold this matrix along the diagonal, so then this lower part is the mirror image of upper part. When you fold the matrix along the diagonal, then this lower part is negative of the elements of the upper part. So this is what is meant by symmetry and skew symmetry in matrices. Then trace of a matrix means trace of matrix is denoted as a trace of A. It is sum of diagonal elements, sum of all diagonal elements of given matrix. Trace is also defined only for square matrix because diagonal elements exist only for square matrix. Now in this case, see, for this matrix, what is sum of all diagonal elements? Diagonal elements are all 0. So it is 0. So in the first case here in this case, sum of all diagonal elements. Which are the diagonal elements? 1 plus minus 1 plus 2. It is algebraic sum. Means if there is sign also, you have to consider it. So in this case, trace of A equal to 1 minus 1, 0. It is 2. So trace is nothing but it is the sum of diagonal elements of a given square matrix. Now I will solve few problems. Write the order of the matrix. The matrix is given here. Also write A23, A14, A2. So what is the order of this matrix? There are 3 rows and count the column 1, 5 columns. So it is 3 by 5. A23 means element in the second row, third column. Second row is this 1, 2, 3. Third column is this. So second row, third column, it is 6. A14 element in the first row, fourth column, that is this minus 3. A22 means element in the second row, second column, which is 3. Now construct a matrix A equal to Aij, 3 by 2, order is given, and ith row, jth column element is given as modulus of I minus j. So 3, it is of order 3 by 2 means there should be 3 rows and 2 columns. So total elements in the matrix should be equal to 3 into 2, 6. M by n matrix has a mn elements, so here 3 into 2, 6 elements. So find out the elements one by one. A11 is element in the first row, first column, 1 minus 1, which is 0. A12 is equal to 1 minus 2, which is modulus of 1 minus 2. So minus 1 actually, but modulus always gives you positive output, which is 1. A13 is not there because there are only 2 columns. Next go to the A21. So 2 minus 1, I minus j, I first, j next, which gives you 1. So A22 is equal to 2 minus 2, which is 0. Then A31, because 3 rows, 3 minus 1 equal to A32 is equal to 3 minus 2, that is equal to 1. So therefore the matrix A equal to, write the first row A11, A12, so 0, 1, then second row 1, 0, then third row 2. This is the given matrix which has order 3 by 2. The next, so here in this case, write orders and types of matrix. So it is a 2 by 2, order is 2 by 2, it is a square matrix because number of rows is equal to number of columns. So it is of order 3 by 3, square matrix, but here in this case, this is upper triangular matrix because elements below the diagonal are all 0. Now in this case, this is a diagonal matrix because square matrix only, but it is diagonal matrix because elements other than the diagonal elements are all 0, non-diagonal are all 0. So this case, this matrix, this is a lower triangular matrix because elements above the diagonal are all 0. This is scalar matrix because it has all diagonal elements equal. Its order is 2 by 2. This is also of order 2 by 2. And this is of order 3 by 3. Now this matrix is identity matrix because all diagonal elements are equal to 1 and its order is 2. This is a column matrix because there is only one column and 3 rows. And here it is also row matrix, 1 rows and 4 column is row matrix. And this is a rectangular matrix because number of rows not equal to number of columns, 2 rows and 3 columns. So order is 2 by 3. Now 2 matrices are given here. You have to find out 3a plus 2b. 3a means first find out 3a, then find out 2b, then add those two matrices. 3a means every element of a has to be multiplied with the 3. 3 2 is 6, 4 3 is 12, 5 3 is 15. Then 3 3 is minus 9, 6 3 is 8, 7 3 is 21, 3 1 is 3, 8 3 is 24, 9 3 is 27. Then 2b is equal to, find out 2b, multiply every element of b, 6b by 2. 3 2 is 6, 6 2 is 12, 2 2 is 4, 2 1 is 2, 4 2 is 8, 5 2 is 10, 8 2 is 16, 7 14, minus 1 is minus 2. Now add these two elements, 3a plus 2b, which 6 plus 6, 12, 12 plus 12, 24, 15 plus 4, 19, minus 9 plus 2, 7, corresponding 18 plus 8, 26, then 21 plus 10, 31, then 3 plus 16, 19, 24 plus 14, it is 38, 27 minus 2, 25. So this gives plus 2b. Now you have to find out a into b, second question. A into b means finding the product. So I'll write a into b is, first write the matrix A, 2 4 5 minus 3 6 7 1 8 9 2. Then the matrix B, 3 6 2 1 4 5 8 7 minus 1. This gives you how to do the multiplication. First check is multiplication defined. This is of order 3 by 3, this is of order 3 by 3. These are square matrices of same order. Hence, number of columns equal to number of rows. Take the first row and first column, multiply corresponding elements and add up all the result. 3 2s are 6 plus 4 1s are 4 plus 8 5s are 40. Then go to the second column. In the answer also shift to the column. 6 2s are 12 plus 4 4s are 16. Second to the second element. Then third to the third element. 7 5 is a third 5. Then first row with the third column. 2 2s are 4 plus 5 4s 20 plus so 4 5 is a 20 plus 5 into minus 1 minus 5. Then similarly second row first column, come down to the second row, minus 9 plus 6 plus next second row second column, 6 3 is a minus 8 plus 7 sevens are 49, minus 3 twos are minus 6, plus 6 fives are 30, plus minus 7. Then third row first column 3 plus 8 ones are 8, plus 9 eights are 72. Then third row second column 6 ones are 6, plus 32, plus 7 nines. Next, third row third column 2 ones are 2, plus 40. Simplify all these. So after adding up all these together, finally get the result a into this 46 plus 4. Then this is 12 plus 16, 26, 35, which gives 63, and so on. This is how we find the product of two matrices. Next, integral powers of a square matrix. How to find integral powers of square matrix? You have a square matrix A of order n, then a square is obtained using a into a cube is a square into a, or else you can do a into a square also. A power 4 is a cube into a into a cube, or a square into a square. This is how we find the different integral powers of the given matrix A. So suppose here a is given, find a power 4. I'll write a power 4 as a square into a square. So first I have to find out a square, which is a into a, that is equal to 1023 into 1023, multiplying a matrix with itself. So first row first column 1 ones are 1, plus 0 twos are 0, so it is 1. 1 into 0 0, plus 0 into 3 is 0. 2 ones are 2, plus 3 twos 6, 2 plus 6 is 8. Then 2 into 0 0, 3 3 is 9. A square. So a power 4 is 1089 into 1089, multiply together. So again first row first column, here this gives you 1 ones are 1, plus 0 into 8 is 0, 1. So then 1 into 0 0, 0 into 9 is 8 ones are 8, plus 70. 8 ones are plus 9 eights. Then 8 zeros are 0, plus 9 nines are 8. This is the final answer. A power 4 is by a square to a square. Now let's see what are determinants. Every square matrix is associated with a number, real number usually, is called its determinant. Is associated with a real number, it is called determinant. So if you have a matrix which is A of order m by n, then determinant of A is denoted as determinant of A, or two vertical lines like this. That gives you a real number. So here this is a matrix, whereas the determinant of A is a real number, one single value you will get. Now how to find a determinant, how to assign a number to 1 by 1 matrix. So 1 by 1 matrix has only one entry, then determinant of A equal to the given entry itself. Example, if A equal to matrix minus 3, then determinant of A equal to minus 3. If A equal to 4, then determinant of A equal to the given number itself is the value of the determinant of that matrix. For 2 by 2 matrix, the determinant is calculated like this. Suppose A equal to 1, 2, minus 1 and 0. So the cross multiplication method, 1 into 0 and this value. So it is a determinant of A equal to 1 into 0 minus, this minus is fixed, always there, then 2 into minus 1. So 1 into 0 0 minus 2 into minus 1 minus 1 minus of minus plus, so it is plus 2. This is how we calculate determinant for 2 by 2 matrix. Similarly, if you have A equal to the matrix 1 3 minus 1 5, then determinant of A equal to cross multiply, so 1 into 5, minus is always there, then 3 into minus 1, that is 5 minus of minus plus 3, which is equal to 8. Now for a 3 by 3 matrix, the determinant is calculated by the expansion along any of the rows or any of the columns. For example, 1 0 5 minus 1 3 2 4 2 minus 1. So this is the given matrix. It is a 3 by 3 matrix. Now to expand this determinant, find the determinant of A, what you should do is, first I will write the matrix 1 0 5 minus 1 3 2 4 2 minus 1. So vertical line means it is determinant. These square brackets are for matrix. I have to evaluate this determinant. It always has a sign. Every element has got sign. This is plus, minus, plus, alternative. Then minus, plus, minus, plus, minus, plus. It continues. I am now expanding along the first row. Means deleting first row is fixed. Okay. Then go to the first element. It is in the first column. Delete that column. So you will get a, see, I am expanding along, expansion along the first row. You can expand along second row, third row, first column, second column, third, any column or any row. Here expansion is along first row, so deleting first row is fixed. It is to be deleted every time. Now go to the first element. This is in the first column. What is the element? Right, 1. What is its sign? Plus. Then it is in the first column. Delete that column. So if you delete the column, then what you will get? You will get a 2 by 2 determinant. So you have to write that 2 by 2 determinant. I'll write here 3 2 2 minus 1. Done. Now go to the second element, which is in the second column. So delete that second column. So the element in the second column is 0 along with its sign, that is minus. So minus 0 you have to write. Okay, minus 0. Then when you delete that second column, this second column, you are remained with the minus 1 2 4 minus 1. So you have minus 1 2 4 minus 1. Then go to the third entry, that is 5. It is in the third column. Delete this third column. Okay, the element in this first column, I mean first row and third column, is a 5 along with its sign, plus 5 you have to write. Therefore when you get plus 5 into minus 1 3 4 2, the remaining one. Now expand this. 1 into minus 3 minus 4, same as 2 by 2 determinant, minus 0 into, even if you find out it is 0 only, 1 minus 8 plus 5 into, this is minus 1 into 2 minus 2 minus 12. 4 3 is 12, here minus 2. So simplify this, you will get minus 7, this is anyway 0, then it is minus 14 plus 5, that is minus 70. Minus 70. So it is minus 77. This is the value of the determinant. So when you are expanding along the first row, deleting first row is fixed. Go to the first element. It is in the first column. Delete that column. Then you will get the 2 by 2 determinant. Then which is to be multiplied by the first row first column element, which is 1 along with its sign. Then go to the second element, which is minus 0. Delete that second column. Minus 1, 2, 4, minus 1 remains. Go to the third element, that is plus 5. Then delete the third column. The remaining 2 by 2 determinant is this. Evaluate it to get the final answer. This is expansion along the first row. You can expand along any of the row or any column. Answer remains same. No change in the answer. Now about minus and cofactors of elements of a matrix. Suppose you have a matrix Aij of order m by n. Now I want to find out the minors of each and every element and cofactors of each and every element. Minor of element in the ith row jth column, that is minor of Aij, is denoted by Mij, and cofactor of Aij is denoted as Cij. Mij is the determinant. It is determinant value which is obtained by deleting ith row and jth column. Ith row and jth column in which the element Aij lies. Cij is minus 1 to the power I plus j into Mij. That means minor multiplied with the sign of that element gives you the cofactor. Let us see how to do that. A equal 2 minus 1, 3, 5. This is the 2 by 2 matrix. I want minor of 2. So M11, it is the element in the first row, first column. So M11 means delete first row, first column. When you delete first row, first column, you will remain with 5. So minor of 2 is, this is minor of element 2. Okay. Next, M12 means element in the first row, second column. That is minor of element minus 1. So delete first row, second column. You are remained with the 3. So M21, delete second row, first column. That gives you minor of 3. Minus 1. M22, delete second row, second column. That gives you element 2, which is minor of 5. This is how we find the minus. Cofactor is C11, cofactor of 2. Cofactor of 2 equal to minus 1 to the power 1 plus 1 into M11. Minus 1 to the power 1 plus 1 is 2. Minus 1 whole square is 1. So M11 is 5. So C12 equal to minus 1 to the power 1 plus 2 into M12. So M12 is 3. This is minus 3. Cofactor changes here. So you can remember like this. What is sign of 2? Plus, minus, then minus, plus. So therefore C21 equal to, what is the minor of 3, which is minus 1. Minus 1 into minus, so minus of minus plus 1. If you are getting confused, use the formula 2 plus 1 to the power M21, which is minus 1 to the power 3 is minus, and M21 is which gives you plus 1. Okay, the shortcut method is writing the signs, then multiplying the minus by the corresponding signs. C22 is equal to, deal here, M22 minus 1 to the power 2 plus 2 into M22. M22 is 2. This is minus 1 to the power 4, which is positive. So answer is 2. So this is how we find minus and cofactor. So for a 2 by 2 matrix. For 3 by 3 matrix, so it is for a 2 by 2 matrix, this is how to remember the sign of each element, plus, minus, minus, plus. Now for a 3 by 3 matrix, finding minus and cofactors of all the elements, A equal to 1, 0, minus 1, 2, 5, 3, minus 2, 4, 1. This is the matrix. Now I want the minor of the first element, M11, M12, M13 I want. That is the first, delete first row, first column. So you will get 5, 3, 4, 1. 5, 3, 4, 1. Then first delete first row, second column, 2, 3, minus 2, 1. 2, 3, minus 2, 1. Then delete first row, third column. So that gives M13, first row and third column. So 2, 5, minus 2, 4. Now evaluate this determinant, that is 5 minus 12 minus 7. This gives you 2 minus of minus plus 6, 8. Then 8 plus minus of minus plus 10, just 18. So these are the minus. Now if you want cofactor C11, C12, C13, so in that case here minus 1 to the power 1 plus 1 into M11, that is minus 1 whole square into M11 is minus 7, which gives you minus 7 because this is positive. So C12 means you can get the sign of element plus minus plus also, plus minus plus. So here in this case C12 means minus 1 to the power 1 plus 2 into M12. Its sign is minus, so it gives you minus. M12 is 8, so it is minus 8. C13 sign of this element in the first row third column is positive, and M13 is 18, so plus 18. So this is how we find minors and cofactors for a 3 by 3 matrix. For the properties of determinants. First property is that determinant of A equal to determinant A dash. A and its transpose have the same value for its determinant. Second property, any two rows or any two columns are interchanged, then sign of determinant by minus 1. Example, if you have delta is equal to determinant 2, 3, 1, 1, what is the value of this determinant? Minus 2, minus 3, minus 5. I will interchange here these two. Delta dash is equal to, that is 1 minus 1, 2, 3. Without evaluating, directly you can write the value of the determinant as a 5, because if any two rows are interchanged, then the value of the determinant is, earlier value is minus 5, it should be multiplied by minus 1, so it becomes plus 5. So you can check also 3 plus 5. If any two rows or columns are identical, then determinant of A 0. Suppose if you have delta equal to 2, 3, 2, 3, then always it is 0. Value of the is 0. If any row or column is multiplied by a scalar k, then determinant value is multiplied by k. That is, suppose if here for the first row I will multiply it by 2, then the new matrix will be 4, 6, 1 minus 1. Now I have to find the value of this determinant. So it is directly minus 10. You can multiply the earlier value by the scalar 2, that is minus 2. You can check with this minus 4 minus 10. Now the fifth property is that if any row or any column is the sum of two or more terms, then we can write the given determinant as a sum of two or more determinant. Here the first row is a sum of two terms. Every term is a sum of two terms. So I can split this determinant as A, B, C, X, Y, Z, L, M plus the next lambda, mu, gamma, X, Y, Z, L, M. If operations of the type Ri changes to Ri plus Krj or Ci changes to Ci plus Kcj, elementary operations, are applied on any determinant, then the value of the determinant remains unchanged. That is, suppose you have a delta equal to, here in this case, delta is 2, 3, 1 minus 1. I will apply the operation. First row changes as R1 plus 2 into R2. Only first row changes, second row no change. So see, you will, suppose you will get a new determinant, delta 1 you name. So that is 2 into R2, 2 plus 2, that's 4. Then 3 plus 2 into minus 3 minus 2, 1. Then second row as it is. What is the value of this determinant? Minus 4 minus 5. The value of this determinant is also minus 1. So if you have any operations of this form, and when you apply it on the given determinant, its value change, it remains same. So these are the properties of determinant. So determinant of A is it's the same as determinant of A dash. If you have any two rows or any two columns the same, then value of the determinant is 0. That is third property. If you interchanged any two rows or any two columns of a matrix, then the value of the determinant changes its sign, that is multiplied by minus 1. So if you multiply any row or any column by scalar k, then value of the determinant also gets multiplied by k. So these are the properties to be remembered, because these properties will help you to solve the given problems or evaluate the value of the determinant without doing the actual expansion. See here, some problems. Evaluate. This is the determinant. One thing you can do here is evaluating by using the definition method, that is usual expansion method. Even without using that, by looking at the entries and the common factors, what you can do is, I will change here, in this case, this is your delta. Delta is equal. Here, when I add up all the columns to the first column, minus 3 plus 5, 2, 2 minus 0. Similarly, 8 plus 9, that is 17, minus 17 is 0. 3 minus 6 minus 3 plus 3, so 0. Here I'll apply the operation. C1 changes to C1 plus C2 plus C3. That means when you add up all the values to the first column value, that is minus 3 plus 5, 2, 2 minus 2, it becomes 0. No change in the second column and no change in the third column. And this value of the determinant remains same, because using that property, sixth property, the value of the determinant doesn't change even if you apply this operation. So 8 plus 9 is 17, minus 17, 0. Then 3 minus 6 is minus 3 plus 3, it is 0. So if you have any row or any column with all entries 0, value of the determinant is 0. So without doing the actual expansion of this determinant, we directly got the value of this determinant as 0 using the properties of determinant. Now this is equal to, here I am going to apply, see, the operation R3 changes to R3 plus R2. That is because here first row 1 1 1, second row no change, A B C, third row changes as add third row to the second row. Okay, so A plus B plus C, only third row changes. Here also A plus B plus C, B plus A plus C means A plus B plus C. So then using this is property 6. Even if you apply this operation, you will get a new determinant actually, but value remains same as per the property of determinants. Next, whenever there is a same element or same factor in any row or any column, you can always take that factor common outside. 1 1 1, A B C, and 1 1 1, because that factor is taken outside. Now the first row and third row have same elements. Okay, means they are exactly identical, hence the value of the determinant is 0. Using that third property, using the second property, or the previous we mentioned here, if any two, third property, if any two rows or any two columns are identical, then value of the determinant is 0, hence the value is 0. Now to get the value of this determinant here, see the fourth question. This we will write it as 2 5 6 3 4 1. Then the last column is written as a multiple, because there is a common factor. 6 5, 6 is the common factor. So here 6 is the common factor. So 6, when 6 is the common factor, you can take it outside. Then the remaining 2 5 6 3 4 1 5 9 7. Now you can see that this third column is a can be subtracted from the rest 2, that is 5, 3 plus 2 is 5, 5 plus 4 is 9, 6 plus 1 is 7. So 5 9 7, here also you will have C3 minus C2 minus C1 if you do for the third column. So 5 minus 3 minus 2 is 0, 9 minus 4 minus 5 is 0, 7 minus 1 minus is 0. Therefore any row or any column with all entries 0, the value of the determinant is 0. Now in this case, we have to evaluate this determinant, say 2x plus 3x plus x. So here you can do R1 changes to R1 plus R2 plus R3. If you apply any of these kind of operation, value of the determinant remains same. So what happens? 2x plus 3 plus x plus x, that is 2x plus x plus x, 4x plus 3. This value is also 4x plus 3. Second entry, third entry, that is also 4x plus 3. Then you will get x, then 2x plus 3, then x, well you have x plus 3. Now there is 4x plus 3 common in the first row, you can take it outside. then we will get 1 1 1 x 2x plus 3, then x 2x plus 3. Now you can either directly evaluate or else you can use the property, sixth property, so that you can make all these entries below 1 all are 0. You can make them 0 because when you make all these entries 0, then evaluation will be easier. Or else you can make these entries, because here it is unknown x 1 1, you can make them 0 as a c2 changes to c2 minus c1, c3 changes to c3 minus c1, 1 minus 1, that gives you 0. So I am doing that because evaluation becomes easier. No change in the first column. 1 minus 1 0. Okay, 2x plus 3 minus x, that is x plus 3, then x minus x 0. Similarly, 1 minus 1 0, x minus x 0, 2x plus 3 minus x, it is x plus 3. Now you can directly evaluate along this first row, because rest all entries 0, only this entry exists. That gives you 4x plus 3 into x plus 3 whole square, because this value anyway it is 0. This is the value of the determinant. We evaluated this determinant by using the properties of determinant without doing the actual expansion.